Yeah, so the first part 0 is just making sure everybody has an environment set up locally. Go through kind of these 4 steps, making sure that Python 3 is installed, creating a directory for this class in a local environment, installing some packages that we'll use throughout today's tutorial, and then downloading this notebook from the course webpage and launching it. So how about each of you go through these setup steps individually, and then if you have any problem or you encounter an error that you can't figure out, we can both go around the room, and when you're ready with the Jupyter Notebook launched to start the next step, let us know. We'll go on to the next step when we're all ready. The instructions are hidden. Oh, sorry. On this computer, it is on the Windows. I have any number of create environment. So did this, I think it worked when you ran. Oh yeah, the last word here should be activate. Oh, I think I'm everything.
Code source is not recognized as an internal text.
It's not working.
Oh wait, no. That's fine.
That is an operating system. Oh yeah, this is yeah, try and just area?
I'm getting there.
Okay, no worries. This one. You try to make the environment instead of I see. So if you want to activate a conda environment, that's fine too. It's a different stuff. We can also, can I just see what try to environment this way? It says is the not internal external comment and not something to yeah, and are you still getting the same error? Okay, yeah. Then let's look up for you two how to create environments.
So yeah, who are using formula will be different. So this sequence of code works on my Mac locally. Are the both of you using Windows?
It's totally fine to make an environment through Conda a different way. This is just so you have like a place where throughout semester you're installing packages for this course, and maybe if there's a different course where you're installing other things. Yeah. On the Anaconda docs, I see Conda create new -- name and then the name of the environment. On the activate, yeah, so that succeeded. Yeah. So for people who are on the installation step, has that worked successfully? Okay. Has anybody launched the notebook already? Who's still going through the steps?
Running out of space.
Okay, on your computer?
Yeah, so I keep deleting stuff.
Oh. So is there more problems for Ben? Yes.
Gotcha. I think that was our sequence back and forth. Yep. So that is
Interesting. Also not happening.
launching. We will download some other data sets and models, so maybe creating a little extra space would be gigabytes. the other approach to making an environment. It's,
It also doesn't make.
okay. Gotcha. Might be a way to just do the activation differently on Windows if it succeeded in creating the environment.
I was going to say that there is a way to add.
Oh yeah, you could just do it. I think I have an approach.
This is fine. There's.
You can do ls to see if it's created. Maybe create another directory. So it's, or is this the directory that you just created?
No, just.
So maybe make a new directory in here for the class materials. Yeah. So now we run this again. Yes, there's another easier way to activate it actually. Awesome. So now you just do period / and then the name of the environment. No space after. And then do the same and big thing / bin / activity. Oh, sorry, a space. So add a after activate period EAT. It should like
Yeah, but I was supposed to do those.
If you replace bin with scripts. Okay. The data. I think you just have to, we'll get to this in a second. Yeah, we'll do it together, but I think you just have to like make an account and accept the competition rules. Which are all about like, the competition is already in.
It's on the course web page.
What? Okay.
Yeah.
Did you have a question for the specific part of the thing that you did?
I mean, I like making counts, so it's just.
When you do the download of all. I think it's just that. No, I believe it's not. If you want to, the people, is anybody else waiting still on one of the steps from the environment setup? Maybe I will start, so I'll start describing the data and stuff while your installation finishes, and just give me a signal if you have a problem with another part. Does that sound good?
Yeah.
So yeah, today, the kind of data setting we're going to use to go through this example data science machine learning workflow is toxicity classification. So this is something that will come up in some of our later lectures and exercises too, as an example of an application where there has been a lot of research on bias and fairness problems in predicting toxic comments. So today we're not gonna talk about those problems specifically. We're going to do the workflow of kind of building a toxicity model, so then we can appreciate some of the other findings in future lectures. And like it's a legitimate, it's like an important application to try to predict and classify toxic comments, because if you're like a newspaper, the New York Times, or a social media platform, there are a lot of toxic and problematic comments that might get posted to your site. And this is something like content moderation is something that many platforms have to engage with. So it's not one of these like applications where you're like, maybe you shouldn't be doing that at all, right? Like maybe predictive policing or something. Like this is something that I think most of us would agree it's valuable to be able to label comments as toxic or not. Okay, so some background on the data that we're going to use. Where did it come from? I think it's really important to think about how this data was produced, who collected it, where did it come from, to make sure you think about those questions before just like using something or studying it. So this data set was made publicly available by conversational AI team from Google. So they had created some toxicity detection models, and then about 5 years ago, they sponsored this competition on Kaggle, which is like a website that runs data science competitions. They offered a pretty nice prize. I forget how much it was, but asked people to use a data set to try to build better models for toxicity detection. And the data they shared, I think, it's around 200,000 comments from Wikipedia pages that human annotators had labeled for toxic behavior. And so this data set does contain text that is offensive and vulgar. We're not gonna, in this notebook, none of that text will come up on the screen. We're not gonna look at specific examples, but if you were to go through the text on your own time or do a project with it, that's a warning that they highlight on the site. Okay, so the first step is to download this data from Kaggle and unzip it into the same directory where you have the notebook. Maybe we can just go around and give me a thumbs up if we have downloaded the data. Yes. So there's, yeah, it will unzip into 4 zip files. Is that what you're asking?
Yeah, so download.
Yeah, there should be like a download all button on the data tab of the website.
Unzip the inner files as well?
No, you don't need to. We're still waiting on the data download.
Like all it takes me like the rules page.
Yeah, just,
And then it'll take me to like.
I think then just go back to the data page and download.
Okay.
Yeah.
They should fix the redirect when you accept the.
It's download all on the data tab. You make an account.
I think you make an account, you accept the competition rules, it sends you to the settings page, and then you.
They have like 20,000 ad blockers in there, so I did not see the settings page. You'll have to trick.
Okay. Rules flagged as a question site. Okay. All right, so I'm going to go on to the first section of this, where we're going to just do some exploratory analysis of the data. Okay, so a thing that I usually do when first getting a data set is to just manually look at some of the examples in the data. I think it's even worthwhile to do more of this and to like get a feel for what's in the data, to do even more than we'll do like in this example today. But we have some comment text, kind of paraphrased you at all, Gary. And then we have some other columns here. So can anybody tell us what our input variable would be for the task of toxicity classification? Exactly. And what are our outcome variables? You know what I.
Is it like the level of constant?
And do you mean like all of those columns are one variable, or do you think each of those columns represent a separate variable?
Yes.
Yeah. Yeah, exactly. Yeah, each of these columns represent a separate field that one of the labelers might have assigned to a comment. And what kind of outcome variables do you think these are? Like, so if we have binary outcome variables, what kind of task would we be doing? Is it classification or regression? So another useful thing to look at when you're exploring a data set is, so we have these binary outcome variables, but you might assume that more comments are benign than are toxic. So how many positive examples do we have? Okay, we have a fair amount of positive examples, but the fraction of comments labeled as one of these things is less than 10% and less than 1% for some of these. So we have a pretty imbalanced set here. And feel free, but you can run this on your own. The idea is you run it on your own computer as we're going.
Are you using like a file or the kernel?
Not sure what you mean.
It's never used street group.
Oh, is it the top right?
There's like also option.
I see.
Environment show.
Yeah, so it just created like a new notebook that you could use as well, but you can also just edit the one you downloaded. So this has, you can run the code directly, yes. And there, so for people who haven't used Jupyter before, I should have given a quick explanation. There should be like a set of buttons on the right side or somewhere where you can press this play button to run the cell you're in. There's also a keyboard shortcut if you do Shift Enter, that will also run the cell. Okay. So what are some ethically relevant things about this data set that we don't know based on what you've seen so far?
What exactly qualifies as these things, and like, for example, for identity behave, what types of identity have they?
Yeah, we don't even know how the annotators were asked to label these things. Like what was the sentence that they were told to think about before applying like identity hate? Which identities did it cover? Any other thoughts?
I think the first two columns, the toxic and severe toxic, I think there's no clear boundary between these two. So I don't know how they label it.
That's a really good point. Yeah, it's not, you could imagine that being one variable that had 3 ordinal levels, like non-toxic, toxic, severe toxic. But that's not how it's coded, and we're not sure, were they labeled independently? Or did they actually like break up a 3-level variable into 2 binary labels? Yeah, we're not sure. What's the difference between those? So another one that I was thinking of is we don't know who labeled these, right? Were these Wikipedia editors? Were they crowd workers on a platform like Mechanical Turk? We're not sure who labeled these. So whose perspectives come through in the Any other comments on that? Okay, cool. So the first, after doing some of this exploratory data analysis, we're going to comment a little bit about evaluation before moving into some of the modeling approaches. And I think it's really important to think about, before doing any modeling, how would you evaluate that model? This is something we'll really think about when it comes to fairness and bias, like what other metrics should we compute to measure bias and to make strong claims about it. But it also comes up for just understanding if the model works in the first place, like can it do the task it claims it does? So we are going to split. Well, first of all, we're just going to take a little sample of these 200,000 comments. We'll just take 10%, 2,000 examples, so we can, examples can run in a reasonable amount of time here. And then we'll split that 2,000 into half in a training set and half in a validation set. Does anybody know what training and validation subsets are? Can anybody tell us why it's important to do this step? What do you mean
Well,
overfitting?
if you train on the data to 6%.
Could have an accuracy measurement.
Well, yes,
It might
it's
just
gonna
not
be
be. Right. Yeah, I think Avijit drew an example in one of the first lectures where if you had one parameter for each data point, you could just memorize the exact, draw like a classification boundary that went around each point, but was not very
Generalizable.
Right.
So it will not like scale across future examples if we overfit. So yeah.
This brings us to our first homework question. So how we're gonna do the homework from here is I've integrated little cells that have a question for homework, and you can just put your responses like in the notebook. So meaning you could just type text in this same box, or you could create a new cell and type. You don't have to do this right now. This is like to do before class on Tuesday. But that's how, like, that's the format we're imagining for turning the homework in. Is you can just directly do it.
Yeah, and then the whole note.
Yeah,
Is it
completeness.
as a Jupyter notebook
As a-
or as a
yeah.
PDF?
As a notebook.
The
Also,
PDF
that-
recommendation.
That reminds me, sorry, for PDF homeworks, I think you didn't know this, but there's an overleaf template that I always share. So in the future, you can just edit that for the homework.
Okay, any other comments before we go on to a first modeling approach? So the first thing that we're going to think about is our input data are these comments, right? Just a sequence of Latin characters, and we need to convert them into some numerical representation that the computer can understand. This is necessary, like, for any type of model that we will be using to represent toxicity classification. So if anybody has taken a natural language processing class, it's fine if you haven't, but maybe the simplest representation of text is something called a bag of words. It's kind of what it sounds like. If you have a comment, you treat it as a bag of the different words that were in the comment. So you have a possible vocabulary, right? Maybe every word in the English language, or at least every word in this comment data set. And you represent one comment as, oh, this comment contained words like 6, 9, 10. So we can apply this representation to our training text examples. So what this function did here was it took our inputs, the comment text, and split it into comments for training and comments for validation. And it took our outputs, the toxic label, we're just going to look at this one label, and split it into labels for training and labels for validation. So that's why this represents our text. Column of our text examples. Okay, so how many words were there in our vocabulary? 9,000. Here is one of the comments. Now you knew that revert mooring is disruptive. This is maybe very Wikipedia specific. The thing to think about is like, how well will a model trained on Wikipedia generalize to other contexts? And here is its bag of words representation. So we have this matrix. There are, this is a vector. There are 9,135 positions, one for each vocabulary word. And there are only 14 elements that are ones, right? So these 14 words, everything else is 0. So this is a very sparse representation. So now that we have some numerical representation of our input, that this was text here, but it could be images. In different example, it could also be just like proper numerical data, meaning like a continuous feature like the length of this desk or its height or its width. So the second part we're going to think about is, so we've decided how to represent this input, the comment text. But now we want to model what is the probability or the likelihood that something's toxic given a specific comment. So one simple model for binary outcomes is called logistic regression. To give you a little visual about how it works. When there's just, so this is showing in just 2 dimensions. Logistic regression is very similar to linear regression, but the extremes of the data are truncated to be 0 or 1. So you can just output, your prediction is just 0 or 1, which is like the structure of the labels we have here. Have people seen logistic regression? Any questions about that?
I'm not forgetting that. Is there something, for some reason the penalty is none, or
That's a great question. Yeah, so in scikit-learn's implementation of logistic regression, by default, it actually runs a regularized version, which is, I forget if it's lasso regression or ridge regression, but it runs a version of logistic regression where it also adds a penalty term to the parameters to say, let's fit a model that doesn't put like too big of a weight on any of these parameters. And so the default vanilla logistic regression, you have to actually specify is none. That's just a artifact of this scikit-learn library. Okay, so we can train this model on our data set, our bag of words representation of our comments, and our labels. And now we have a model that was fit to our data. Okay, so let's go through one more section and then we can take a short break because it took a long time to get set up. Okay, so the first thing, again, evaluation is really important, especially if you're doing research like auditing a system or measuring its biases. Maybe all you're doing is evaluation. Maybe you're just downloading a model from some other company, or that's you're auditing internally for a company, and you're testing how it performs on maybe data you collected or examples that you think it might fail on. So it's really important to think about evaluation. And some of the metrics today that we're going to look at, it will help us, it will be a good foundation for understanding fairness measures and metrics, because they build off of these kind of global metrics for how a model is doing. So first, maybe the simplest way to evaluate the model is accuracy, right? Just what percentage of predictions did we get correct? Okay, so this is 93%. Seems really easy. What do you think? Is this good performance?
How many? It's properly categorizing the a lot of positive. Likely I'll just put most of that as positive. As many negative examples. Or the rest of that, if not really. That was confusing.
No, I see what you mean. And how would you connect that to our example here, where we saw there was only 1% of some categories labeled as like toxic. I probably didn't phrase it well. So we saw in the beginning that like for this toxic category, most of the labels were 0, like non-toxic.
Yeah.
And only 10% were ones, toxic.
So it's probably predicting all of them as like not toxic. The ones that are toxic might not really be predicted. We can't tell this.
Exactly. So that is exactly what we're going to test in this next line is, well, what if we did like the simplest thing you could do? We have a model where we just predict 0 every time. There's no parameters. That would actually be 91% accuracy. So this is important to always think about like what is the kind of simplest, dumbest thing that you could do, and make sure you understand what that baseline is before you interpret something as like, oh, this is really good, but actually this should be our kind of like baseline. But I think the other thing that you were saying about accuracy is like maybe there are other problems with this measure. Like even if we had a balanced data set, maybe we care more about like the positive labels, the toxic comments. So this leads us into, let's look at some other metrics that are important for assessing binary classification. And these especially will be useful for understanding various measures. Okay, so the first one is precision. Has anybody heard of precision? Yeah, you want to try to describe it?
Yeah, I'm kind of forgetting what the difference is, but I recall I think it's your way on. But in like terms of like the medical field, like I think it catches false. It's just more false negatives, I think. Alright, so doing a good job articulating this. Please try. I got it last semester. Okay.
Oh, yeah, so recall. So yeah, let's maybe start with recall here. So recall is the fraction of true positives divided by the fraction of true positives and false negatives, which means like all the actual positive things. So recall, if you like really try to optimize recall, you're going to try to identify like as many toxic comments as possible, or meaning any toxic comment you miss, you get penalized for. You're trying to find as many, you're trying to identify, like label things as positive, make that fraction as high as possible, what you labeled as positive divided by all the actual positives that were out there. And then precision, on the other hand, it's focusing on the true positives. How many comments did you correctly label as toxic? But the denominator is true positives and false positives, meaning everything you predicted positive. So here, if you're really focusing on precision, you would get penalized when you made an incorrect prediction, an incorrect positive prediction, like you incorrectly called something a toxic comment, because then that would be a false positive. And you could get a really good precision if you were really cautious, right? And you only called things toxic that you were really confident were toxic. That might make it more difficult to get a good recall because you have to be a little bit more, I guess, kind of like confident for recall, like make a lot of guesses.
Sure. So the recall is like 1 minus type 2 error.
That's a good question.
With type 2 errors, you
I
predict the correct data wrong. So 1 minus that is that you got correct if that one is correct. Right?
Okay, that, yeah,
I mean, yes.
I know that
Time
we-
to error is recall. There is the.
yes. Yes. Awesome. You know that this table has all of the things, and so I just wanted to look at it, yeah. False negative rate and recall is 1 minus the type 2 error. Okay, so looking at precision and recall, now we have some more nuanced metrics. We see that our precision is 0.6, meaning of the things we call toxic, we got 60% of them right. And our recall is 53%, meaning of all the comments that actually are toxic, we correctly identified 53% of them. So this paints a less rosier picture than this number, but maybe a more honest picture. Okay, so now I'm interested in people's opinions, maybe connected to like health applications. In this specific application, identifying toxic comments, which do you think is more important? Why?
Because like, if you're really precise, then you might miss a lot of comments.
But it seems like it would be a really bad thing if a bunch of toxic comments were left on your article, and maybe you got, you identified 2 correctly, you didn't make any mistakes, but you let 100 go through. But yeah, there's a strong motivation for recall here. Anyone want to defend precision?
Well, I actually love precision because I'm finding something that wasn't actually toxic. Because then you're penalizing something that wasn't like wrong. Instead of like, I mean, if it wasn't like classified as toxic, it most likely wasn't that bad. I'm guessing I hope that that's how it works because it can be like kind of weird. I would say precision is.
So this connects to some of the fairness work, I mean, both comments really do, on this topic, but yeah, where people have found that comments from maybe certain groups are much more likely to be labeled as toxic. And so if you were really trying to identify anything that was remotely toxic and take it down, then maybe you would have a lot of false negatives. False positives. Yeah. And you would remove a bunch of things that were like legitimate discussion, people using a word, like repurposing it, or engaged in like conversation about something, and those would all be removed. So I think you can make good arguments for both of these metrics here, and the larger point is like the evaluation metric that you are using for a specific situation, you really need to think about like, what do we care about here? What is most important for the thing I'm working on? That can be really meaningful right there. Like if you're evaluating something that was focusing on the wrong metric, and you just like point out that that's the wrong metric and make a good argument for something else, have a whole different perspective on that.
And I want to add 2 more comments. So we will see later in the course that mathematically you can't optimize every metric. So you have to make design choices, which is why I made the comment like while starting the course that bias is often a design problem because it totally is dependent on what design you chose. The second thing is sometimes the solution is also a design problem and not a machine learning problem. So on social media, eventually what people have started doing now is instead of removing comments, they put a warning label on it and hide it. So they're not fully removed. So if something has been misclassified, you as a user have the agency to still click and see what it was and report if it was incorrectly mislabeled. So basically what I'm trying to say is sometimes solutions go beyond just improving your model. It could also be a UX. It could also be a public engagement. So as we go deeper into the class, we think about projects, also think about solutions that are not purely mathematical. Yeah.
Definitely. Yeah. Okay, and so this leads into the second homework question that you're going to work on, which is doing a little bit of research on another metric that one might use to evaluate a binary classifier, do a little bit of plotting, and explain how all different metrics are related. Okay, so why don't we take a quick 5-minute break, and we can spend the last half hour looking at some other modeling approaches with language models and it looks like that for reason all of the individual files are like in this top level directory. And on my computer, they were like nested within here. So if you just remove this, load this directly.
I think it's because maybe this.
This is a different file to this.
I think so.
Okay.
Because I think I'm gonna.
Yeah, do you want to try it right here? Yes.
See the next.
30.
Okay, are people ready to jump back in for the last two sections? Any questions or challenges running things that you want to ask about before we keep going? Awesome. Yeah. Okay, so modeling approach 3, we are going to modeling approach 2, we're going to replace our bag of words, the simplest representation we could think of, with one of the like exciting new representations, a representation from a pre-trained language model. So even if you haven't taken a natural language processing or machine learning class, I still think it's useful just to see what it looks like to interact with these models through Python. There's a company called Hugging Face that has kind of a good name. they have a really cool, a good like machine learning ethics team, and they really focus on making these models accessible, like hosting them on their hub of models and making it really easy to download like a BERT model or the GPT. Now, those models might be really large, especially some of the recent ones, so we're going to work with slightly smaller ones, but this is just to say that that's a really good resource, and it can be, even if some of the stuff in this section is like new or you haven't seen it before, hopefully it's still useful to connect some of like the comments from last lecture to like code examples of what's happening. Okay, so maybe it's a little confusing what like vectors from a pre-trained language model means. This blog post is, if you want to dig more into like the structure of these language models, this blog post is something you can check out. I'm just going to use it right now for this sketch. I think is helpful overview. So the first step in training like a large language model is this pre-training on most of the internet or large amounts of text, Wikipedia or books or Reddit or other sources. We don't have to focus on like the specific internal structure of the model. We're just going to treat it as this complicated black box that was trained on these sources. And we can use the representations that it produces for a specific like comment or a specific string of text. What a lot of research has found is that because these models have learned to accurately predict the next word in large quantities of data, the representation they produce is useful even for other tasks. But what this sketch makes a distinction between is there's the pre-training step, which the semi-supervised pre-training step, which requires maybe lots of data and a lot of compute power and a lot of RAM and space. But that is something that like maybe a different company or open source team or collective of people is doing, and we can still access this BERT thing. That's what we'll do today. But what this BERT pre-trained model doesn't give us is actually a classifier. So when you give like some text to the model, it produces an output, which is like a representation. We'll see what that looks like. It's also a vector, similar to the bag of words vector that we saw. It will have different things in it, but that's the same format. But then the classifier is a separate thing. That's something that a person would need to train for their specific application. So in this sketch here, it's spam versus not spam, email spam detection. But for us, it's going to be toxicity classification. You want to make any comments
Yes.
about that? Go for it.
So to connect this entire thing with what we discussed on Tuesday, remember towards the end of the class, we talked about image reconstruction and how the innermost layers learn deeper representations than just colors and edges. So, and like if we were to make an analog for language models, the deeper layers of word probably have more information than just what a bag of words would contain. Like it probably has concepts, right? It probably has some sort of semantic meaning. And so just extracting those innermost, or sorry, deeper layers, so probably like the second last layer is what is used, is a better representation than bag of words because it's condensed and it just has more complex concepts. And so we will use those as inputs to the classifier to see if we get better performance than just bag of words.
Yeah, one concrete example of structure that the bag of words representation could not pick up on is if you just shuffled all of the words in your sentence. You get the exact same representation. It would be the same bag of words. So any meaning that's conveyed through the order of words or the way that they're paired together would be lost in that representation. And so the specific model that we will use today is a slightly distilled or shrunken version of a model that Microsoft trained. This is related to the BERT model, but basically they made it smaller, removed some of the parameters, so it runs a little bit faster, but it still has 33 million parameters, so it's still a very large model. And this is a nice thing about Hugging Face is they have a lot more information about the paper, where a model came from, its results, what it means. You'll see this. We'll use one of these model cards. Okay. So when you run this cell, this will download the model, which will take a few seconds if you haven't run it yet. Or if you have, like the second time you run it, it will just load it locally from where it's now stored on your machine. This also downloads something called a tokenizer. I am not an expert in natural language processing, but this is a thing that's necessary to pre-process the text, the raw input text, before you pass it to the model. So this is the first thing that you have to do to be able to use this pre-trained model, is we have to turn our raw text comments into tokens. There's a few pre-processing steps. First of all, we're truncating them at 100 characters. So this is something right here. If all the toxic information was like after 100 characters, actually I think this is words. If it was after 100 words, then we wouldn't. So here there are 30,000 tokens in BERT's vocabulary. After we have converted the text into tokens, this is what it looks like. So if you remember, our comment was revert boring is disruptive. So you see there are, it has converted these different words or sometimes subwords into a specific number. And then it has added zeros, which are meaningless. So we can pad every comment to the same length. That's just a nice step. So we can like process multiple comments at once through the model. They need to be the same input length. But what this attention mask tells us is it tells the model, ignore these padding tokens, right? That's not actually part of the thing that we're processing. We're just doing this so we can process multiple at once. So this is the pre-processing before we give the text to the model. I think for natural language processing people, there's a lot that goes into actually how you design these tokenizers, what vocabulary is, stuff like that. That we're not going to go into. I don't know much about. So now that we have converted our comments into tokens, we are going to turn the tokens into vectors. These are the representations that actually utilize the things that the pre-trained model has learned. The kind of relationships between words or phrases. So this step will take about 30 or 40 seconds, at least. That's how long it took on my computer last night. And it takes a little while because this was a model with like a lot of parameters, even the scaled down smaller version. And this is a trade-off between some of these bigger models and like the representation we used before, right? It took like no time at all to make our bag of words representation. Does anybody have any questions about this this content so far? Or we wait for it to finish? Okay, it looks like it finished, which is nice. So now we have these vectors. I can show you just what one looks like, so you know kind of, I think it's helpful just to see like what this actually is. So this is just a long array of floating point numbers, like decimals. There are 384 dimensions, right? So it's actually a lot more compressed than our other representation, which had 9,000 dimensions, had one for like each word in our vocabulary. Also a limitation of that is like it would struggle when you had like every word language to represent. These representations are actually much denser, more compressed. Okay, so now we can fit the same model, the logistic regression, but using this alternative representation as the input. We use our same output. This step doesn't take very long to run because this is actually a smaller representation, a more compressed one. And now we'll see how our predictions, what our predictions look like with the model trained on this other representation. This step will also take a little bit of time because we have to do the same process of passing the comments, the validation text through the pre-trained model, this vectorized function. So this will take another like 30 seconds or so. Okay. We actually see that we didn't do quite as well with these features from the more complicated large model. Does anybody have any thoughts why?
That the comments stuck of the author are pretty like particular. And so like the back and forth other sources could be structured differently. There's comparisons.
So we are using the same, like our validation data is also the Wikipedia comments
Or
here.
like the data that we're using.
Yeah,
That's the
exactly.
same.
No, not
Okay.
necessarily. That's
Okay.
that's what you were saying.
Yeah.
Gotcha. Yeah. Yeah, that's an awesome point. Right? The BERT model wasn't specifically pre-trained to look at toxicity or Wikipedia, like Wikipedia comments. And so maybe it actually doesn't, like the representations it produces are not as effective as just like a bag of words representation, where maybe there are specific words that often in our data set, like always identify toxic comments. I think also connected to that is because we have a very small, we filtered down to just 2,000 examples, like a small set of this big data set. Maybe there are specific, like very specific words in this small sample that have strong correlations with the outcome. And so this simpler representation can do well. And this might not be the same if you did this whole workflow with all of the data. My intuition would be that this retrained model does perform better, but just to say it's not like, yeah, it's not guaranteed to. So yeah.
Is there like, I'm getting different numbers in the logs.
Yeah. So there's also that will come up a little bit in the homework. There's like randomness in some of these models if you don't fix specific like random seeds in your book. So you might get results.
So, I mean, off the top of my head, one thing people do inside neural networks is this thing called batch NOR. So while going from one layer to the other, they shuffle the inputs so that it generalizes better, which means that you will never get the same exact output every time you run. So an example of randomness. That's why often people will freeze particular layers if you don't want them to change, or you fix the seed. So numpy.random generator generates a new seed every time. If you force it to always generate the same random number, the new model will always generate the same. But yes, machine learning models are probabilistic processes and not deterministic. So unless you force it to be the same output every time, it will be slightly different.
Yeah, there is a way to make it deterministic.
Yes. By default, it's not.
So there will be 2 homework questions related to this section. The first is having you try using actually the full BERT model. This take a little bit longer to do the vectorization, but it's interesting to compare maybe the results you get with that model compared to this like smaller one that we did in class, and also just to show how it's not too difficult to access like these language models that get talked a lot about, like BERT, right? It's a common example of one, and you can use this exact same process to play with it. And then the other thing is to look at BERT's model card and answer some questions about how it was trained, what it was trained on, what kind of text, what kind of languages, what could be some problems or biases based on that. Okay, so the last example we'll do is connected to some of the potential limitations of just using the representations from a model like BERT, like out of the box, meaning just using them without modifying them or updating them at all for your specific application. So it's common to fine-tune or update a model specifically for the classification or prediction task that you're working on. So to go back to our diagram of what is happening with the pre-trained BERT model. So this is something that happens in this side of the diagram when we're doing supervised training on a specific task, toxicity classification with our labeled data set. So there are different approaches, and I'm by no means an expert in fine tuning. I think there's a lot of even research on how to do this most effectively. But the approach that we did first, in like approach number 2, was we just learned a very simple classifier. We didn't update any of the parameters in this big model, like to try to capture some of the correlations in like Wikipedia comments, or specifically Wikipedia toxic comments. But we can also do that. We can try to update, not just learn the parameters of this little classifier, but update some of the ones in this big model. Okay, so that's what we're going to do in this step. So you'll see we're using the same model as before, this pre-trained model. And we're just using a slightly different class from the transformers library, which adds, this is the whole complicated network, and we've just added one classifier layer at the end. So now that's what this model for sequence classification with 2 labels does. This will be a neural network classifier instead of a logistic regression classifier. But yeah, I wanted to show what was actually happening. And they helpfully tell us, hey, some of the weights were not initialized from the model you downloaded. They are this classifier weight, classifier bias. You should probably train this on a downstream task before you use it for predictions and inference. So that's exactly what we're going to do. It's actually very cool to see this. Like this is representative of Hugging Face's approach. Is like really make sure people know what they're using, but also make it very easy to use like some clear things. Okay, so this cell isn't super important. It's just some.
I just think. What is classifier?
Yeah.
Oh, in my bedroom?
So what the classifier weight and classifier bias reference are the parameters of this specific part of the neural network. It's not like, I don't think it's necessary to like know exactly the functional form of those parameters. You might learn that in like a deep learning or machine learning class, but it just references when we add this model, like this one classifier layer, there are parameters that have to be learned to map the 384 dimensions of the vector representation to just 2 output classes, like toxic or non-toxic. And none of those have been yet. They are just random initialized. Is that getting at what you're asking, actually?
Yeah.
I wonder if you have any.
Yeah, so like maybe we could draw what's happening here so that it's helpful for everybody. So imagine like blah blah blah, the entire BERT layer with this whole thing is neural network, this is BERT. And the last layer has 384 neurons. Or like this, whatever way you want to represent neurons as. And we want only 2 outputs, like toxic or non-toxic. So essentially what we're doing is adding another layer, which is strongly connected. So each of these are connected to the place. Similarly, each of these connected to this. And this will become our final output. Because we just added this layer, none of these edges have any weight, it's just random numbers. So now we will retrain this whole thing on our comments data so that these weights are learned. And also like, I don't think the bird is frozen in here. So the whole thing will be learned, but because we added this, which is completely uninitialized, completely untrained, just initialized with random numbers, we are getting that comment.
So in theory, could you like freeze all the layers before that?
Yes,
And
yes.
then just train it on.
Yes, there actually is a function called freeze for PyTorch. And people do that all the time. Like we add massive networks that will take a long time and computation to train. So we freeze certain layers or maybe the whole BERT network and only train this. You can freeze particular layers if you want to.
Okay, so is everything, the reason we're able to run BERT without like massive views or whatever, like, is because everything's really compressed.
Yeah, we're using the smaller model, right, which runs on local machines.
We are, but one of the homework questions will use the full model.
But BERT is not as big as like GPT that you cannot run.
Okay.
BERT is still like runnable on a computer.
Yeah, it's actually substantially smaller in terms of, I think the main limitation with some of the recent models is just space on your computer, and BERT is, I forget how big the file is when you download it, maybe a gigabyte or 500 megabytes.
Was that helpful?
Does anybody else have questions?
If it would be helpful, I think I could send a document that describes what these things are, like what dropout means, what pool means, what activation means. Like, do people know these concepts in machine learning? I could send a helpful refresher. I'll email some after the class.
I was also treating this as like, you don't have to fully appreciate how all of these, like, probably aside from the authors of the paper and people working directly on it, like how, like why this whole architecture looks exactly like it. So what this cell is doing is just to do this fine-tuning updating process. You have to put your data into a specific class that PyTorch requires. PyTorch is one framework for training neural networks. So it requires you to use this dataset class and define your own custom class. And then create a data loader, which is just basically batching some of the examples together, meaning like so they can go, so you can pass them through the model like multiple at a time instead of doing one by one like we did. Start running this while I describe it. So I've tried to add comments here for what each line signifies, because we talked about kind of the machine learning or neural network training process. We didn't really talk about it at a low level at all. But just so these comments identify what each line of the code is doing. This is a variant of stochastic gradient descent, which was the optimization algorithm that was referenced in the last lecture, which is how most, all neural networks are trained. This is one specific variant of that optimization algorithm. Here, this line is passing the text, the inputs through the model, making prediction, toxic or non-toxic. Here is calculating our loss on the prediction. This step imputes which nodes in the network were responsible for the loss. That's through an algorithm called back propagation, which is key for how neural networks are trained, but it's basically just a chain rule. This step actually updates the model parameters. You just take one step, the direction that basically improves our performance the most. And then this just kind of like resets that optimizer. So this will just take a little bit longer. A couple minutes when I was running it on my computer. And if you did this step with like the big BERT model, it took about 10 minutes on my computer to do a full fine-tuning pass. This is also, sometimes people do multiple. We did one pass through 1,000 comments. Sometimes people do multiple passes through if you want to like train the model more. And we're not gonna, it's not a machine learning class, so we're not gonna go into like maybe how you would decide when to stop this process, but that's cool. Okay, so the last thing, we'll just make predictions using our new updated fine-tuned model and see how those did. And this last homework question is something that came up, is some of you might already have noticed, like when you were running it, you got slightly different results to what I got. And so if you, basically think about why that happened. I guess we talked about it in class, so you could reference some of the stuff we talked about or do some other research and add some more.
Yeah, we did.
I was running fine, so.
Yeah, mine also.
I'm not give this answer.
No, this is actually like, the model was updated and it seems to be making absolutely terrible predictions, is what's happening. It predicted everything as non-toxic. So.
Wait, is that, I got precision as 1.
Okay. So it seems like this could be an example of, it would have been better to actually maybe only like update these new parameters, maybe not do so much updating. Again, this is to show you an example of like what the pipeline looks like, but I'm not an expert on, or we would have to dig into more like how should we be specifically fine-tuning this model for this example. Okay. So I know it's 2 minutes after. Any final questions? I can also stay around for like 10 or 15 minutes if people have more questions about this or the homework, or you want to show what your scores looked like on your.
I think there is some error because I didn't get this error and I got actual numbers.
I did too last night.
We'll get improved precision. They're local machines.
I got a higher position than you got for your phone.
I got the same.
So think about why these might be different at a high level, but also maybe think about there are some specific lines in the code where things we set caused it to have non-deterministic, or things we didn't set caused it to have non-deterministic.
So to your point, Shefali, I think freezing word would have been more helpful because when I've done this in the past, when you try and fine-tune a whole massive model like that, the amount of epochs we have is not enough. You need to train it for a far longer time to properly learn the new embeddings. So freezing word as it is, but only training the last layer probably would work better.
Is it always the last layer when you add something for each week?
You can chop off wherever you want. That's what I'm saying. So PyTorch is very cool because it lets you, look at individual layers, and you can probably decide to, look at basically, let's say this is layer 30. So you freeze everything up to layer 30, and then you redirect the outputs of layer 30 into your own new hyper network, and then you train from here onwards. So you never use, you can if you want. When you print the output of a model, it shows what the intermediate layers are, so you can cut it off at any time and just write your own forward function. Do we have a forward function here when you defined it?
No, we're just using the.
Okay, but yeah, you can look up PyTorch tutorials. You can define your own forward function, which basically shows what the forward activations are. So you can have this whole thing as a frozen module and write a new forward function for the rest. And this is helpful because we often want to use knowledge from older models that have been trained on massive data, but want to train on our very specific small subtasks.
Would be interesting